Hello. This lecture will cover pages 76 through 78 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Operational Amplifiers, Chapter 4F, Analyzing Operational Amplifier Circuits. Before we start working some problems here, I want to start on page 76, Analyzing Operational Amplifier Circuits. If you can identify an op-amp circuit as one of the three simple configurations we discussed in the previous lectures, just use the gain equations as shown as I gave them to you and solve the problem. Don't try to reinvent the wheel. However, when the circuits become more complex, the procedure that I've given you here is key to analyzing those circuits. This is the procedure to analyzing most operational amplifier circuits. It's only a three-step procedure. So what I'd like you to do is have this page 76 out and ready to look at when we work through these 6 problems here in this particular lecture. Notice that you do your initial analysis at the V plus node to determine the V plus voltage. Now, sometimes that V plus voltage is just given to you, like it's been given to us in a couple problems we've done so far. Other times you have to determine it through a voltage divider or some other technique that you've learned in a previous chapter. But you have to start with finding the voltage at the V plus node. Then you project that V plus voltage to the V minus node for the reasons we discussed many times over the past 3 lectures. Then you write Kirchhoff's current law equation at that V minus node to solve for the unknowns. That's simply the 3-step procedure. Before we start working some problems, I told you that the first thing you're going to have to do is recognize what type of configuration you have. And if you look at the 2 of the homework problems here, I want you to notice here that here's homework problem number 4-9. Take a look at it. And here's homework problem number 414. A quick look at those 2 different configurations may lead you to believe that they're different circuits, but they're not. Both of these circuits are non-inverting amplifier circuits. Both of them are. So make sure you can see that. These are the same circuit, just drawn differently. Where we're going to start here is on page 77 and 78. I have blank sheets for you there. There's enough room to do 3 problems on page 77, enough room to do 3 problems on page 78. So what I'd like you to do in your book, if you take a look, this is on page, in my version of the textbook, it's on page 159. But first thing I want you to do is look at problem E41. There's the problem right there. I want you to find I.O., this current I.O., and in the textbook they show it flowing down. I.O. is flowing in that direction. Now, if you want to take the previous procedure that I've shown you on the previous page, and you want to take this 12 volts and you want to project it down to here, which puts 12 volts down here, and you want to place that 12 volts there, and you want to assign 3 currents here, maybe a current in that direction, a current in that direction, current in this direction. You want to use Kirchhoff's current law and write a nodal analysis at that point right there, a nodal equation at that point, and solve for V out, and take V out and divide it by 10K to give you I out. You can get your 8.4 milliamps. Or you could simply just look at that circuit and determine what type of circuit is it? Is it a non-inverting amplifier or an inverting amplifier? Go right to that gain equation, find V out, divide it by 10K, and get your answer. I'd like you to stop the video, work that out, and see what you get. I would do this in class, but since I have to rely on these video lectures, here's my solution to that problem. There's my solution in its entirety. I want you to notice a couple things. I want you to notice I redrew the circuit so you could see it. I wrote nothing but equations here, and I wrote logical equations. That's what I expect on your exams, that's what I expect on the quizzes, and that's what I expect on your homework to get full credit. You have to be able to work out your engineering problems like this so people can read them and understand them. Make sure that you understand every step here to my answer of 8.4 milliamps. The second problem I want to look at is this problem right here. It's problem E42. E42 says determine the gain of the op-amp circuit in this figure. Well, we've done that in class. This will probably be the last time you'll ever have to do it in your career. But what I want you to do is I want you to go ahead and project this voltage from this point to this point. It's Vs right here. Go ahead and assign a current there. Call it I2. Go ahead and assign a current there. Call it I minus. Go ahead and assign a current there. Call it I1. And write your nodal equation at that point. It's going to be in terms of Vs and V out. Form the ratio. That's the definition of the closed loop voltage gain. And see if you get the answer up here. Try that on your own. Next problem we're going to look at. Well, I did that. I worked it out. So just make sure that there's my solution to it. Here's my solution. Notice I laid everything out for you. Labeled everything. Was very neat. At node 1, I defined node 1 up here by Kirchhoff's current law. There's my initial equation. Very carefully, I went ahead and made sure that these parens were in, so I distribute this negative sign because some of you are going to miss that, and it's going to cost you. It's about the third time I told you to be careful when you write these nodal equations. In any event, you work down through here, and this is the solution. AV closed loop is equal to 1 plus R2 over R1. The next problem is E43. Here's E43 in my textbook. Determine both the gain and the output voltage of the op-amp configuration shown here. In this case right here, you could write a nodal analysis if you want by projecting this 1 millivolt right there and writing a node equation there. But maybe you can just recognize that as a non-inverting amplifier circuit. Get the gain, take it times this, get your answers. That problem you can do in your head. Make sure you know how to do these problems. These simple ones like this. They're easy points on an exam or a quiz. How did I work the problem out? E43. You should try it on your own, but this is what my solution. There's my complete solution. Again, no chicken scratching here. Very clear and understandable. That's what I'm expecting for full credit in my engineering class. E44. Looks like that. What they want you to do is find current I1, I2, I3, and I4 in this circuit. I1 flows left to right, I2 flows out, I3 flows left to right, I4 flows down. Using the techniques I've shown you, stop the video and try this on your own. Try to hit that wall that some of you are going to hit working this problem out. And then learn from my solution. If you work the problem out, E44, I redrew the circuit, showed all my currents. By inspection, you should see that I1 is 0 amps. That's 1/4 the problem already. You got it right. I1 is 0 amps because we're assuming an ideal op-amp. That's infinite input resistance. No current I1 can flow there. And if you're using the technique, which you're going to have to use to solve this problem, of projecting this voltage down to this point or this voltage to here, that's not volts. That's current source. You can't project current. If this is 1 milliamp current source and it flows into that node there and absolutely no current can go in this direction because it's essentially an open circuit, infinity ohms, do you realize all 1 milliamp of that flows down this way? And if you have 1 milliamp flowing through 5K, that puts 5 volts at that point right there. You can just get rid of all this out here and just put 5 volts there, and it's a simple problem. A lot of people don't see that. But these are the techniques you're going to have to understand and recognize in that toolbox of yours to do well on my exams and quizzes. I'm not going to give you problems exactly like some of the simple homework problems. You have to be able to analyze this that way. And it doesn't take much to do that, but it takes practice. If you take a look, therefore, you get 5 volts at that point. I just looked at that circuit and didn't even write a nodal analysis at that point. I recognized it's a non-inverting amplifier circuit, and I come up with the gain. The gain is 1.5 using the ratio of the resistors 1 plus 5K over 10K. I found V out of 7.5 volts, and then using simple analysis techniques, I can find V3 real easy. I can find I3 very easily. It's a negative 0.5 milliamps. I can find I4 very easily. And then by Kirchhoff's current law at node 2, I can find I2 very easily. They're the answers. I1, there's I3, there's I4, and there's I2. You should be able to work that problem as well. Problem 4.5. Here's problem 4.5 in the book. Looks like this. Very good problems. 2 stars on this problem. Find VO in terms of find V out in terms of V1 and V2 in this figure. Here's V out, here's V1, and here's V2. I want you to find what the output voltage is in terms of V1 and V2. Well, if you take a look at this problem, use your design techniques we have back there on page, or your procedure back on page 76. This isn't a problem like you've seen before, so it falls into a more complex circuit. But if you follow the 3-step procedure, this is a pretty easy problem. I want you to start down here, and I want you to work that problem out and see if you can't get the solutions that they have up here. Try problem 4.5 on your own. Stop the video, and I'll show you my solution then. My solution on this problem looks like this. I have to start with finding the voltage at the V plus input. Well, here's V2, and this is no more than a voltage divider rule. That voltage V plus is nothing more than V2 times 7K divided by 11K. The K's cancel. So V plus is equal to V2 times 7 divided by 11. 7 divided by 11, that's the voltage here. You can just erase all this. Now you know the voltage at that point. It's 0.636 V2. Put that voltage, project it up onto the V minus input, which puts it at this point. This is all the same point. This is all the same point here. So all I do is Kirchhoff's current law, a nodal analysis at that node. I have I1 coming in. I have I2, I showed them going down. There's I minus, and there's I3. There's 1, 2, 3, 4 currents in this node here. There's my simple equation. There I solve for the actual currents in my second step. Again, I would show the first step. You get credit for that. Make sure you put these parentheses in or you're going to miss. Students miss that minus distribution every time. This is I1. Look at the circuit. This is I2, look at the circuit. And this here is your I3, look at the circuit. Obviously I minus went to 0 here. Least common denominator was 20K. I multiplied through by 20K, cleaned that up. Here's my expression. V out is equal to negative 2 V1 plus 3.5 V2. V out in terms of V1 and V2. They said if V1 is equal to V2, which is equal to 4 volts, find V out. V out is equal to 6 volts. If the operational amplifier power supplies are plus 15 and minus 15, What that mean? That means if VCC is plus 15 and VEE is minus 15 and V2 is 2 volts, what's the allowable range of V1 before your saturation occurs at either rail? Well, there's your equation for output. That has to be less than 15 volts on the one rail. So minus 2 V1 plus 3.5 V2. Well, V2 is 2 volts. So here's your inequality. Minus 2 V1 plus 7 has to be less than or equal to plus 15. That's your one inequality. Here's your second inequality. V out has to be greater or equal to the minus 15 here. Remember? Can't be minus 16, minus 17, or it will saturate. Has to be minus 15, minus 14. It has to be greater or equal to minus 2 V1 plus 7. Greater or equal to minus 15. There's your second inequality, which gives you this range for V1. Minus 4 volts is less than or equal to V1, which has to be less than or equal to 11 volts. Plug in your minus 4 volts in that equation with V2 being 2 volts. And you'll see that's gonna hit right up against the rail. Plug in your 11 volts and you'll see that's going to hit right up against the rail. So as long as V1 falls within this range right here, you won't saturate the operational amplifier. It's a very good problem. You're going to see it again. So look it over. And then finally, I'd like you to look at problem E46. In your textbook. Looks like that. Now, you've never seen a two-stage amplifier looks like that. But you have to analyze that. And I want you to be able to analyze that when you see that in future classes. So basically, where you start here is you can't pick a voltage here and project it to here. I mean, you can't take 5 volts and say there's 5 volts there, because this circuit messes all that up. So what you have to do is refer to this as V out prime. I called this the dummy variable V out prime because this is V out. If this is V out prime, this is just a voltage divider at this point. This is an infinite resistance from here in. So you can just ignore it. So what voltage is at this point if that's V out prime? Well, that point is just V out prime times 5K divided by 5K plus 10K. That's the same circuit as if you would have something that looks like this. Let's see if I have it here somewhere that I could show you. If you just simply had a circuit that looked like this. If you just simply had a circuit that looked like this. Where this here is V out prime. And this is 10K ohms, this is 5K ohms, and there's that voltage we need to know. Well, that voltage at this point is V out prime times 5K divided by 15K. And that's the same circuit you're looking at right here. That's the exact same circuit you're looking at here. That voltage is V out prime divided by 3. Some students call it V out prime times 0.33, but that's too much of a round off to get these answers up here. If you took that out 0.333, you might be okay, but let's keep this as V out prime over 3. That voltage is V out prime divided by 3, and basically you're going to project it up to that point right there, and you're going to write a nodal analysis right there once you find this equation over here. So just hold that for a thought. That's why we find V out prime divided by 3, because we're going to project it to here, and we're going to write a nodal analysis right there. You can write an equation there. Now, if that's V out prime, that's a voltage divider there too. So I'm going to find the voltage at V plus right here at this second stage here. It's just V out prime times 10K divided by 12K. 12.5K rather. Look at that. V out prime times 10K divided by the sum of these two is that voltage there. That's 0.8 V out prime. This voltage here is 0.8 V out prime. I'm projecting it up to here. So I know that V3 is simply equal to 0.8 V out prime, right there. I know that. I'm going to use that later. Now, you know the voltage at this point in terms of V out prime. This is V out on this side of the resistor. Over here, you know the voltage, it's V out prime divided by 3. You can write a nodal analysis right there, giving that current and this current, which goes to 0. So get your one equation there. Get your second equation here. Don't write it in terms of V3 though. Write in terms of 0.8 V out prime. Two equations, two unknowns. You can solve V out's minus 9 volts and V3 is equal to minus 4.8 volts. That's a very good problem. If you can work all 6 of these type of problems on your own here, you should be in pretty good shape for working some of these operational amplifier circuits out. And that concludes the lecture.